반갑습니다, 여러분. 2020년도 음성음운론 5번째인가 6번째인가 헷갈리는데. 반갑습니다, 여러분. 음성음운론 수업을 시작하겠습니다. 이번 시간에는 우리가 조음기관의 그 구조에서 비롯된 조음기관 모형설과 소스 필터설이라고 하는 두 가지 굉장히 중요한 이론을 소개하고, 그 다음에 이제 그 음향 음성학적인 어떤 그 자음과 모음에 대한 분석, 설명을 하고, 그리고 숙제를 내고, 뭐 이런 순서로 수업을 진행하겠습니다. 다시 한번 강조하지만 이 조음기관의 그림을 잘 숙지하시기 바랍니다. 자, 두 가지 이론을 생각해 볼 수 있는데, 첫 번째가 조음기관 모형설, 두 번째가 소스 필터설이라고 하는 겁니다. 다른 게 아니고, 이제 우리가 조음기관이라고 하는 것을 한쪽이 막혀 있는 튜브라고 생각을 하고, 그 튜브를 울려 가지고 나오는 음향학적인 어떤 웨이브, 음파를 이제 모형으로 우리가 사람의 성도를 이제 흉내내어서 만들 수 있다는 겁니다. 그렇게 해가지고 공기를 불어넣으면 인간의 말소리와 유사한 것들이 발음이 될 수 있다. 이게 이제 거의 그 앵무새가 말을 따라하는 원리죠. 사실은 소스 필터 이론이라고 하는 것은 이제 성대에서 나는 소리, 그것을 이제 원음이라고 하고 F0라고 하는데, 그것이 성도 조음기관 보컬 트랙을 나오면서 필터링이 된다는 거죠. 그래서 소리가 컬러링이 된다는 이야기입니다. 자세히 보도록 하겠습니다. 그러니까 조음기관을 이렇게 단면을 우리가 봤을 때 이것을 일종의 튜브로 생각할 수 있다는 거죠. 그래서 한쪽이 막혀 있는 튜브. 근데 이제 여기서 이제 공기가 나왔을 때 여기를 울려서 나는 음파를 이제 생각하는 겁니다. 그래서 이제 소스 성대에서 나는 게 F0가 되겠고, 이제 여기가 F1, F2, 그 다음에 이제 뭐 어떤 공간들 비강 F3, 뭐 요 앞에 조그만 입술 앞에도 나오는 이제 입술강이라고 생길 수 있겠죠. F4 뭐 등등을 생각하는 것입니다. 그 다음에 또 우리가 중요하게 생각해야 될 개념이 이 부분에서 기본 기초 개념이 그 포르만트라고 하는 겁니다. 그래서 스펙트로그램에서 음향 에너지가 집중된 주파수 대역이 까만 띠 모양으로 나타나는 것인데, 포르만트가 있는 주파수 대역은 음향 에너지가 비교적 높은 강도를 가지고 있다는 것을 의미합니다. 모음은 제1 포르만트, 제2 포르만트, 제3 포르만트까지 나타나며 발성 형태에 따라서 제4 포르만트, 제5 포르만트까지 나타날 수 있습니다. 음형대, 음형 주파수라는 용어로도 사용되었으나 최근에는 포르만트로 사용되고 있습니다. 그래서 이게 음향학, 음향음성학, 에서 중요한 개념입니다. 사운드 스펙트럼에서 이 포르만트를 볼 수가 있습니다. 자, 저음 기관을 이제 인위적으로 본떠서 만든 기계라고 할 수 있겠죠. 그것에 대한 그거 실험을 보도록 하겠습니다.
これは人間の声道を柔らかい舌で実現した模型です。この模型ではここに歯があってここに舌先が見えているのが分かります。この模型では舌を含む声道の下側の壁面がすべて柔らかい素材でできています。後頭側には穴があってここから音源が入力されます。これは笛式の人工口頭です。まずこの人工口頭だけで鳴らしてみます。それではこの人工口頭を先ほどの声道模型に入れます。そして鳴らしてみますとこのように手話に近い中声母音がしますが、今からさまざまな声道形状を実現します。まず奥の下の方を押しますとちょうど咽頭付近の空間が狭くなります。そして舌を大きく下げて、ちょうど顎を開く状態を作ると母音の「あ」になります。次に声道の前方で作られる音をお聞かせします。先ほどの咽頭腔の狭めは元に戻して逆に声道の前方において舌を上方に押し上げ口外に当てますと舌の上面には中心線に沿って溝があるため狭い空間を細長く作ることができます。これによって母音の「い」を作ります。次に母音「い」よりも少しだけ舌を下げますと母音「え」になります。舌を上げたり下げたり何回かしてみます。最後に母音の「う」を作ってみたいと思います。声道が直角に曲がるあたりに、狭い箇所を作って、母音の「う」を作ってみましょう。このように舌の位置をいろいろ変えることによってさまざまな母音を作ることができます。
어떻습니까? 잘 보셨습니까? 저런 물건을 하나 구입해 가지고 실제 이제 보여줘야 되는데 아쉽습니다. 어쨌거나 이제 조음기관을 이제 처음에 성대를 만들어 가지고 공기를 불어넣고 그 다음에 성도 보컬 트랙 안에서 제일 큰 이제 장애인 혀를 이제 뒷부분 뒤혀 쪽을 이제 압박을 가해서 그 페링스 인두벽을 좁게 하니까 어떻게 됩니까? F1, F2가 변형이 오죠. 그래가지고 아 소리가 나고 앞쪽을 하니까 이 소리가 나고, 그죠? 모음의 어떤 그게 이제 그 공간, 그죠? 그 공간을 나누어지는 경계를 가지고 이제 F0, F1, F2, F3, F4의 어떤 포르만트가 나온다는 겁니다. 그러니까 이제 파워가 있고, 그죠? 발동부에서 공기가 올라온다. 그러면은 이 발성부, 이게 소스가 되겠습니다. 이 소스에서 이제 유성음으로 이제 아까 세팅을 했죠. 모음의 경우는 다 100% 유성음이니까. 그래가지고 이제 이 필터, 좋은 보컬 트랙에서 혀의 어떤 위치에 따라서 공기가 좁힘이 일어나고 공간이 튜브가 분할이 되면서 그 공간을 레저넌스, 울려가지고 소리가 필터링이 된다는 이야기입니다. 그래서 이게 이제 1960년대에 판트라고 하는 이 유명한 분이 이것을 이론화시켰던 것입니다. 그래서 원음에서 일어나는 것이 이제 우리 소리는 모든 주파수의 소리는 배음이 있습니다. 하모닉스라고 하는데 하모닉스 그러한 것들이 이게 이제 소스 필터 소스에서 나오는 거가 필터링이 되어 가지고 이제 배음을 가지게 되고 그 소리들이 합쳐져 가지고 우리의 아예 이오우 말소리들이 된다는 이야기입니다. 재밌죠? 그걸 기본으로 하고 다시 우리가 모음에 대한 이야기를 해보겠습니다. 이건 이제 보편적인 모음에 대한 이야기입니다.
Vowels have a fully developed formant pattern and can be classified on the basis of their first two formants, F1 and F2. These resonance frequencies can approximately be associated with the size of two cavities separated by a constriction in the vocal tract. F1 with the size of the pharynx and F2 with the size of the oral cavity. Let's compare two more vowels to illustrate that. Cardinal vowel 1, E, with a front constriction, a large pharyngeal cavity, and a small oral cavity, and cardinal vowel number 5, O, with a back constriction, and thus a much smaller pharyngeal cavity and a relatively large oral cavity. And now look at their spectrograms. Cardinal vowel number 1 is characterized by a low F1 value at around 400 Hz and a very high F2 value at around 2500 Hz, whereas cardinal vowel number 5 has a slightly higher F1 value at around 600 Hz and a much lower F2 value of around 1000 Hz. Here are the spectrograms of all 8 cardinal vowels. E, 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 A, O, O, U, U. In plotting the frequencies of F1, the vertical axis, against the frequency of F2 on the horizontal axis, we find a pattern that is remarkably similar to the cardinal vowel chart. Yet, the match is not exact because the articulatory cardinal vowel chart is based on the point of the greatest tongue constriction, whereas the acoustic chart takes its data from all vocal tract resonances. Let us now identify the vowels within more complex spectrograms. In our first example, we can clearly identify at least two vowels. The first with formant 1 and formant 2 very close together, thus it must be a low vowel, such as A. The second vowel involves a transition. The first part is clearly a low vowel again, with F1 and F2 close together, and in the second part, F1 and F2 are drifting wide apart. So the result is a diphthong, in this case, I. And here is a solution. I said sunshine. Note that the nasal consonants also involve some sort of formant patterns, yet they are less well developed. Here is another example. Again, it contains two vowels. The first one looks like a front vowel with an F2 value of around 1600 Hz, hence or are likely candidates. The second vowel must be a diphthong with a high vowel offset such as E and an onset similar to our first vowel, so A is a likely candidate. And here is the result. I said earthquake, where our two vowels are surrounded by fricatives and plosives. So the identification of vowels within complex spectrograms involves the identification of a clearly defined formant structure and the extraction of the frequency values of F1 and F2.
자, 여기서 카디널 바울이라고 하는 이야기를 나왔는데, 뭐 별거 아닙니다. 우리가 IPA 차트를 이제 인클래스 시간에 공부를 할 텐데, 벌써 했는지 모르겠지만, 다니엘 존스라고 하는 이제 영국의 언어학자가 이제 이 얘기를 했던 거죠. 그래서 혀가 이제 인간의 말소리가 구체적인 말소리가 아니라 가상의 어떤 이제 모음을 생각한 겁니다. 그래서 이제 모음 사각도상에서 카디널 바울이라고 해가지고 몇 개의 이제 기준점을 제시를 한 거죠. 그것과 비슷하게 이제 나오는 것을 우리가 보았습니다. 영어 모음의 경우에. 그래서 그러한 것들, 그 다음에 이제 포르만트를 이제 F1, F2, F3 이렇게 나타내지 않습니까? 그래서 그것의 패턴을 보고 이 모음이 어떤 모음이구나, 이제 그런 것들을 우리가 짐작할 수가 있죠. 스펙트럼 분석이라고 하는 것이 음향 음성학에서 중요한 부분입니다. 이제는 뭐 이제 컴퓨터 프로그램이 아주 쉽게 널리 사용되고 있어서 굉장히 편리하게 되어 있습니다. 자, 이번에는 자음에 대한 분석을 보겠습니다.
In articulatory phonetics, consonants are classified according to the parameters place and manner of articulation and voicing. For an acoustic classification, we use frequency patterns, portions of silence, and we know that consonants have no clear-cut formant pattern. The first and most obvious parameter that allows us to identify consonants is the absence of vocal fold vibration in voiceless consonants. In a sa, there is no visible vocal fold vibration and thus no fundamental frequency. A za, by contrast, involves vocal fold vibration and thus has a well-defined fundamental frequency. This allows us to differentiate between voiceless consonants and any other voiced sound. The type of consonant, whether voiceless or voiced, can be classified by additional acoustic properties. For example, all plosives such as a pa, a ta, and a ka involve a significant portion of silence and a short portion of friction noise when they are aspirated, the so-called burst. The characteristic feature of fricatives such as a fa, a sa, and a sha is the clearly marked portion of friction noise. And according to the frequency range and intensity of that noise, fricatives can be kept apart. Other consonants, such as trills like ara, can be identified by regular patterns of vibration and small closures in between. Or they even have visible formant patterns like nasals such as ana or approximants like awa. Yet, the formants are not as clear-cut as in vowels. Consonants influence their environment. Look at these two vowels, a and e. In isolation, they have a steady formant pattern. However, if we put a k in between and say aki, we have an additional narrowing in the vocal tract which alters the shape of the central resonance chambers, the pharynx, and the oral cavity. So, consonants considerably influence the formant patterns of the vowels with which they occur. This effect is referred to as formant transition. Let us now identify the consonants within a more complex spectrogram. Clearly, in this example we have at least two fricatives without a fundamental frequency. They both involve high-frequency friction noise and must therefore be voiceless alveolar fricatives. Furthermore, we have three portions of silence, again without fundamental frequencies, so we have three voiceless plosives. The first is almost unaspirated since it involves a very short burst, the second is well aspirated, and number three, even though it occurs finally, is also aspirated, which means that here we have additional friction noise. In fact, we have two velar and one alveolar plosives. Furthermore, we have two vowels, a high vowel and a low vowel, and a devoiced alveolar approximant with low frequency friction noise, and a nasal consonant with a clearly identifiable F0 but no clear-cut formant pattern. The result is what I created for you, a screencast.
자, 프라트를 소개하겠습니다. 프라트는 말소리의 음성과학적 분석을 위한 컴퓨터용 공개 소프트웨어입니다. 암스테르담 대학교의 파울 브루스마와 다비트 베닝크가 개발했고 꾸준히 업데이트 되어 있습니다. 여러 운영체계에서 실행이 가능하며 사운드 카드가 있는 보통의 PC 환경이면 어떤 컴퓨터에서나 사용할 수가 있습니다. 마이크를 이용하여 모노 및 스테레오로 녹음할 수도 있고 IBM 호환 기종에서 사용하는 웨이브 파일이나 맥킨토시에서 사용하는 확장자 AIFF 파일을 불러서 사용할 수도 있습니다. 또한 이 프로그램은 조음 합성을 포함하는 음성 합성도 지원합니다. 이 프라트라고 하는 말은 네덜란드 말로 말소리를 뜻한다고 합니다. 이 프라트만 하더라도 한 학기 강의용이기도 합니다. 인클래스 시간에 이것을 우리가 직접 시연을 하면서 할 수 있는 시간을 가지면 좋겠습니다. 많은 여러분들은 이제 이게 음성 한 번쯤 다운을 받아 가지고 자신의 음성 연구를 해보는 시간을 가지면 좋겠습니다. 그래서 여러분이 특히 음성 연구를 안 하시더라도 뭐 노래라든지 뭐 또 다른 기타 응용하실 수 있는 부분이 많이 있을 겁니다. 그래서 아주 유용하고 공짜로 이제 다운 받을 수 있고 그러니까 꼭 그 해보시기를 권합니다. 자, 플랫 사용에 대해서는 여러분들이 직접 구글에서 플라트 를 치시길 바랍니다. 플라트를 치시면은 여러 가지 플라트가 아니라 플라트 사용법을 보시면은 양병건 교수님의 그런 이런 책이 전자 출판되어 있습니다. 그래서 이거를 보시고 이걸 더불어서 이제 동영상을 보시는 게 중요합니다. 그래서 이렇게 쭉 찾아보시면은 여러 가지 이제 다른 공개 강의도 있고 그렇습니다만은 음향 분석을 위해서 일단 시간이 되는 대로 많이 시도해 보시기를 바랍니다.
안녕하세요. 원광디지털대학교 언어치료학과 임석인 교수입니다. 오늘은 말과학 두 번째 과제인 플랫을 이용한 음향대 분석하기에 대해서 강의하도록 하겠습니다.
네, 그런 것도 있고 다양하게 있을 수 있습니다. 그런데 이 유튜브에 가시면은 플랫에 대한 것이 더 괜찮은 게 있어요. 그래서 내가 찾고 있는 것은 이거보다도 제가 아까 시청한 것 중에 이것이 제일 무난한 것 같아요. 그래서 참고하시기 바랍니다.
As you're trying to follow those written instructions. So here I have two files that are not the same as I've assigned, but they're examples of a prolonged ah and a connected speech sample. And I've just saved them here on my desktop so that they're easy to find. So the first thing I want to do is open up Prot, and I'll move this over. Actually, we don't need this window at all, so that you can better see what I'm doing. So first thing I want to do is open those files, and I'll go to open and then read from file. Be careful not to choose this next option, open long sound file, since that might make some of these analyses not possible. So be sure to use that first option, read from file, and then I'll go to my desktop, scroll down here, or up until I find, there they are, those two files, and I can actually open them at the same time by holding Control and then clicking both of those files. Okay, I have them both selected, so then I can go ahead and select open here. to put them both here in my objects window. Now I'm going to start with the prolonged vowel first. And the first thing you want to do is use view and edit and take a look at what you're doing, since there might be other things going on in the sound file that you might not want to include. So let's listen to this one. Alright, so if you could hear that in the background, this particular sound file has a speaker that's not able to prolong the ah very long. So we have little bits of ah here, and we just want to select one to look at. So maybe we'll try this one in the middle here and see how that works out for analysis. So I want to highlight that portion and then hit the select button here at the lower left corner. All right, and that gives us an ah here that we can play again to listen and make sure it's what we want. And although he's got a voice break here in the middle, maybe we should include that if this is typical of his productions. So if I go here and go up to this top menu here, I have this whole selection here selected because it's highlighted in pink here. It may be a different color in your computer. But usually when you select a portion of the sound file, it'll be highlighted some color. And since I just want to look at this part, not the whole thing, I can go to File and then Extract Selected Sound, and you want to choose this second option here where it says Time from 0. And that just means that we're just going to cut out this little chunk and start here at the beginning of that sound from 0. Not that we're going to preserve any time information from the original file. There's no need for that in this case. Alright, so then I can close this window, and there'll be a new sound here in my object window that says Sound Untitled. I could always give it a new name. I could click Rename there at the bottom and call this, for example, something like Trimmed just so that you don't get confused as new objects get added here. So we'll give it a name. And then if we do view and edit, it should look just like that selection we had before. So if I click here to play this total duration of the sound, it should be just the same as what we had before. So now it's ready to analyze. So one of the first things we want to do, I've sort of set up a little thing here where these are all the things I'm asking you for in terms of numbers. And we can start filling in the numbers here for the sustained vowels portion. So I'm going to go here back to our object window, and I have the sound selected, and I'm going to go to Analyze Periodicity to get some of that pitch information. So first I'm going to create a pitch object by clicking on that button, Analyze Periodicity, and then going to the option to pitch, the first one. And this little dialog comes up, and for any of your cases, there's no reason to change any of these numbers. They should work just fine. And then you can just click OK. All right, and then everything sort of jumps away for a second, but you'll see if you go back to your object window that there is a new object called Pitch Trimmed Ah. And if I view and edit it, it looks like this. And all it does is it gives you something that you could manipulate if you wanted to, let's say, change the pitch and then add it back to the sound. And it sounds something like this if you click one of these lower buttons, where it's just Prot is reproducing a synthesized version of this person's pitch. And you can see this little portion here where Prot couldn't analyze the pitch is still there in the middle. Let's say you had something incorrect where maybe there's one of these little, sort of pinkish looking dot is up, and it's somewhere up here in the 500 or 400 range, and that doesn't sound right for what your client is doing, you could always just select that portion to eliminate it from analysis, and go here to selection and unvoice, and then it's gone. But we don't really need to do that. We'll undo those last two. Actually, it won't let me redo both of them, so we'll just redo the unvoice, so that little extra thing I added there isn't included. All right, so next we can just go to query, and there's some extra pitch info that we can get just by going to pitch info and looking at this box that comes up. So one of the things I'm asking you for is pitch sigma, or standard deviation. When you talk about pitch sigma, usually you're assuming you're talking about semitones, which is given here. But you could also report the standard deviation in hertz, which is what I've just highlighted here. There are other types of measurements for the standard deviation. Here's one in MEL and ERB, but we haven't talked about those, so you can ignore those for now. So I am going to report it in semitones here. So what the information I want is 1.24 semitones. So if I go to this little box I've set up here, I would want to write here that I have 1.24 semitones. All right, and the other thing we could do is look at the average fundamental frequency that I've highlighted here. That information is also reported in this window if you go here and look at this average section. And PROT gives you several different ways to report it, but for our purposes, it's more helpful to have the average given in hertz. So this first option is the most useful number for our purposes. So 169 point something something hertz is what we'd want to do. So I can just take that little bit of information and paste it right here in my document. All right, that doesn't cover everything you'll need to do for your sustained vowel. So we also need jitter, shimmer, and HNR, which isn't included in that little window here. So we'll close that and this pitch object and go back to these objects here to get that information. So the first thing we want to do is go back to our original trimmed sound file and create a new pitch object. So we're going to go to Analyze Periodicity and then to Pitch CC. This is important. It's a different way of calculating that pitch object, and we're going to need that. So choose that option. It's slightly different than what we had before. And it's okay to say okay to all these numbers. All right, and again, the window sort of pops away, so you have to go back to your PROT object and find it again. Okay, and then what you have to do next is using the control key, or whatever the equivalent is on a Mac, is if you hold on that key and click two of these objects at the same time, you will get a different menu here to the right. And we want to do that so that we get this button here that says 2-point process CC. And that's what you're going to click next. And then it's going to create something else here. And that new object is called point process, and then it's going to have this new name here. And the last thing we're going to want to do is select this sound, the second pitch object we created, and that point process all at the same time. So you're going to have to use that control key again, or whatever you have on the Mac, to help you select more than one object at one time. And then you see once you have all those objects highlighted, that again over here to the right, the options change and you have a new button here for a voice report. And that's exactly what we want. You can go ahead and click on that button and it'll have some options, which those are all good for your purposes. And so you can go ahead and click OK. And then we have this new info box that will open with all sorts of new information. So you can take this and actually collect a few numbers here, not just, you'll see you have jitter, shimmer, and harmonicity or our harmonics to noise information, but you also could get your average and your standard deviation here, but unfortunately the standard deviation is only given in hertz. So that's why I go ahead and have you do it that other way. But in terms of numbers we want for our for your voice report would be just those certain options here under jitter. You'll see there's lots of different ways to calculate jitter, but in order to make sure that you're comparing it to the right type of norms, like the ones I gave you, you want to use these options here that just have local in parentheses after the name in terms of jitter and shimmer. Here, so it's always going to be the first option for each of these types of measurements. So we're going to select here the jitter is 1.069%, and you can simply copy that and paste it here into wherever you started your report. So there is your jitter, and here is the shimmer number we want to use, just the one that has local in parentheses after the name shimmer. So it's 4.088%. I'm just going to copy and then paste it here into my Word document. And the last number I want is H&R, or harmonics to noise. So I want to take this number here. The other one that you have the option of using, or one of the other ones, is noise to harmonics ratio, which is just the inverse, but I haven't given you norms for that. So this number is most helpful, the 19 point whatever dB. So I'm going to copy and then paste it here into my Word document. All right, so that finishes off everything for the sustained vowel, and all we are left with are things that we need from our connected speech sample. So I'm going to close this info box, I don't need that anymore, and go back to the object window here and go to my connected speech sample. And it's always a good idea again to do view and edit and trim, select some portion of the connected speech sample that you think best represents the client's speech. Since there may be more, there may be the clinician talking in the background, or other things that might cause you not to want to use a particular speech sample. Let's say, for example, this looks like a little blurb of speech. If I listen to that, it sounds like that's the patient, judging by the quality of the speech. And that actually sounds like a good place to go. So I'm going to just go ahead and select that for sake of not taking too much time here, and take a closer look and use that for my analysis. You'll want to spend a little bit more time examining each part of your connected speech sample. And here, judging by this one, there's a few things that might be a little bit off here. And I'm going to crank up the volume a little bit so we can hopefully hear that on your end. Alright, so he's talking about the cookie theft picture. You'll have that a lot in your speech samples, likely, since they were all taken the same way. And it looks like here there might be areas where, judging by his voice, he's not having dramatic pitch breaks like Pratt's pitch contour seems to indicate where I've circled. And there's also this little blurb here that doesn't even seem to correspond with a voice section, but either you can include this or you can try and correct the pitch object, which is more complicated. My advice at this point, you can include these errors and just account for that in your report, and that would be good enough for me. It's going to be hard for Prot to calculate some of these values because of these voices are so disordered. This one is a particularly extreme example. Yours may not be this bad. But as long as you say, well, this might be elevated or that might be elevated based on what you saw, that is, just exactly what I'm looking for. That you can look at some of these values and determine whether they are reliable or not based on your knowledge of speech science and voice disorders. Okay, so I'm going to erase that. And we're going to go ahead and use this section of speech, despite those problems I mentioned before. So I'm going to highlight where the speech is, and I'm going to trim that then from the larger sound file. So again, you can go to File and extract selected sound with the time from 0. And if we close this, we'll see there's a new sound here. And this is what we're going to use. And if we click View and Edit, it should correspond to what we just had earlier. All right, so we have the pitch contour. Those are those blue lines here throughout the speech. That's good, but we're also going to want some intensity information. So if you don't have a yellow line in this sample, you want to go to Intensity and select Show Intensity. And then you'll see a yellow line pop up on the spectrogram. If you don't have the pitch contour, you can go to Pitch and then make sure that Show Pitch is selected. And then you should have that blue line on there as well. Now that the intensity contour is showing, we can ask Prot for that average intensity that I asked you for, the mean speaking intensity of conversational speech that you can use to make judgments about whether this person is speaking appropriately loudly, that they're loud enough to be understood. So if you go to intensity and select Get Intensity, or you'll see there's a shortcut option here at the very right, hit your F8 button. Either way, if you do that, you will get this little info box popping up. And you can take that value and cut and paste it into your report. So here his average intensity is about 64 dB. So I'm just going to copy that number and paste it into my document here. All right, other than that, I have a range that I want to know from his lowest fundamental frequency in hertz to his highest, and the pitch sigma or standard deviation, and the average fundamental frequency. All that frequency information is left. So I can get that all if I exit out of this sound. There's a lot of different ways you could get this info, but the easiest would be just to create another pitch object and get all that information from that pitch info option. So to do that, I'm going to make sure the sound is highlighted in the Prot object window and go to the Analyze Periodicity button again. When you click that, you get this menu dropping down and you'll want to select To Pitch. Hit OK, and then if we go back to the object window, we'll see we have a new pitch object. You can hit View and Edit on that and go up to the query window, and here you can either highlight those portions that are unreliable and go to Selection and Unvoice, and they won't be included in the measurement, or you can keep them in and account for that in your final numbers. So if I go to Query and Pitch Info, I'll get a new info box that will give me all this information that I need. So let's start with the average. Here where his average pitch throughout the whole thing is 181 and something hertz. So I'm going to copy that number and add it in here or his connected speech sample. Alright, and I'm going to look at his standard deviation, and I'm going to use the value in semitones since this is a little bit easier to interpret. If we just report it in hertz, it's hard to know how much an impact that has on our perception without converting it to semitones. So we're going to choose that value instead, copy it, and paste it here into the document. And the last number I need here is the range. And if you use this info, you won't even need to calculate that. You can use this column or line of information here, and this time I explicitly ask for it in hertz, so that way if you have the average in hertz, you can compare that to the range. It's just sort of useful background info to have. Highlight that, copy, and paste it into the document here. Alright, so I hope that helps just with getting the numbers. If you need any help interpreting these numbers or run into problems on the way, I'm always more than happy to help you, and it's usually easier in person. Alright, so I hope you found this easy to follow, and just let me know if you have any further questions.
예,
Hi.
뭐 그런 것들도 있는데 다 볼 수는 없죠.
Hello again. In the
그래서
following, I will introduce
그래서-
you to the analysis of sound waves. In fact, there are several ways of
그래서 여러 가지로 이제 그것들을 소개하는 것들이 많이 있습니다. 그런데 무엇보다도 먼저 그 양병곤 교수님의 사이트에 가셔서 플랫을 다운 받아서 거기 있는 매뉴얼을 하나하나 보면서 참고하시는 게 좋을 것 같습니다. 예, 수고하셨습니다.